Section 3.2 is called measures of dispersion. What's the root word in dispersion? Disperse. And what's disperse mean? Spread. So instead of ways of measuring the middle, like mean, median, and mode, we're going to talk about ways to how we can measure the spread of our data. I like to say the range of our data, but the range is actually a way of measuring dispersion, so it's not really the correct term. So just a little note, it says sometimes measures of central tendency are not sufficient in describing a distribution. And so what I wanted to show you guys is an example right here in your book. It's about two universities that both have the same mean IQ. The question is, does that mean they both have students that perform the same on the IQ test, or can we find something more? So I'll just show you, and they did all the data for us, so I'll show you in a second, okay? Here's University A, here's University B with two random data sets, okay? And they were able to come up with a median, or excuse me, the average for both was the same, and I think the average was 100, yeah. So they entered the data into a program that did the bars for them, okay? So if a dean wants to say, my students are the best, they're the smartest, okay? I think University A, am better than University B. We calculate the means and they're both exactly the same. So can I say my students perform better? Well, one way to measure it is with the dispersion. So notice here, they both had a score of 100 as their mean, but it's hard to see. I know it's kind of small. This ranges from 55 all the way to 145, where 100's about here in the middle, okay? But this only ranges from 85 to 130. So in general, which university do you think have the higher educated students, the smarter students?
B.
B. Why would you say B?
Because they start higher in scoring.
Yeah, they're really not very spread out, are they? They're a lot closer, like University A, remember I was the dean for University A. I had someone that got a 55. The lowest person over here got an 85. We don't even know if they got an 85, right? And so this whole idea here is even though these highs kind of outweigh the lows, in general, the majority of the students stayed around that 100, okay? So if you're not as dispersed, you're more compact, you're more consistent, that's a good thing. Another example I read, which anybody a homeowner yet? You guys have to worry about your houses yet? Okay, if you don't, does anybody live at home still? Do your parents make you have to like paint or stain decks or anything like that? You guys are so lucky. Okay, I feel like my parents were slave drivers, okay? So growing up, I had to help stain our deck. And you can buy stains that range in how long they last. So say stain A ranges from 5 years to 25 years. But then stain B ranges from 10 to 20. Which one are you hoping to get? Stain B, because the range, we know it lasts at least 10 years, right? And so their average might be the same, 15 or whatever, but if I get stain A, I might have to go turn around and stain it. No, I'll be gone in 5 years, right? But I might have to turn around and stain it again. So again, that smaller spread, that more compact is a good thing, all right? So what's the first way to measure dispersion? It's the value, the word I've been using all along. It's called the range. The range is denoted with a capital R for either a population or a sample. It doesn't matter. And it's just the difference, okay? So we're going to subtract between the largest value and the smallest value. So to me, I mean, that is the spread of the data, if you ask me, okay? So I just have a really, really baby sample space here, okay? We have these 5 values, and we want to find the range. Well, the range is always high minus low. So my range, what's our high value? 27. And what's our lowest? 17. So that's a range of 10. Is that all right? And I just want to note that this is a spread and not a value. So I'm not trying to represent my values. Notice 10 is nowhere close to any of my values. It's just telling you the spread of my data. So again, maybe this is how much you make per hour or something like this. These are good jobs. There's a spread of $10 per hour. Some people make $17 an hour. Some people make $27 an hour. I'm not saying the average is $10 an hour. It's just the range is $10 an hour. Usually there's units here. And again, my math lab does a horrible job of reminding you of that. All right, so our answer is 10 units there. We have a spread of $10 per hour or whatever it may be. All right, so the next thing, if you have not taken a stats course before, I feel like standard deviation is the first real calculation and real term that you're learning because mean, median, mode, even if you haven't taken stats, you've done it before, all right? So standard deviation is a very good way and a very popular way of measuring the spread of your data. But look at these crazy formulas. Woo! Okay, so first of all, notice that we have two different definitions and two different formulas. The formulas are very similar. The only difference is the population, guys. Remember, population is always measured with Greek symbols. So notice the Greek symbol. That's sigma. That's baby sigma. So remember, the big E was capital sigma. This is baby sigma. I call him an O with a hat. So he has a ball cap on, okay? And I know it's like stupid cheesy stuff, but that's how you're going to remember. You're like, oh, sigma, the O with a hat, okay? Sample standard deviation. Remember, anything that's measuring a sample, guys, is always using our Roman letters, our alphabet. So notice it's the letter S. We can handle that. Let's read the first one because this just kind of piggybacks off of this. So let's see if we can make sense of it. The population standard deviation of a variable, denoted sigma, we already know that, is the square root of the sum of the squared deviations about the population mean, divided by the number of observations in the population. And they're like, oh, that didn't make sense to you? Let me clear it up with this sentence. That is, it's the square root of the mean of the squared deviations about the population mean. Really clear now, right? No, okay? But what I want to do is I want to kind of pick apart the formula and just show you what it's talking about. Does everybody agree that that's the square root that they're talking about? Yep. And what are we doing? We're summing. So that's what sigma is. What are we summing? We're summing the deviations. What's it mean to deviate? Separate, right? So we're seeing how far each of our data values are from the mean. So like, say the average age in this class is 19, but I'm 34. So I'm 15 deviations from the mean. Does that make sense? It's the range, basically. So these are the deviations. Here's my individual data value minus my population mean, right? That's my population mean right there. And there's the squared. So here's the sum of the squared deviations. And what do we have to do? Divide by the number of observations. What's N always stand for? Population size. Whew. So even though there's a lot going on there, we already know what all those symbols are, so we can kind of label them. The next one over, guys, that other sigma, that's called the shortcut method. Doesn't look like much of a shortcut. That is actually how I would teach you probably if we weren't using our graphing calculator. But you're going to quickly see that you never need to use this formula. We'll make a note of that. Okay, let's write that over here. Use calculator. The reason why I'm making a note of that is because today in class you'll learn about the calculator, but later on this weekend when you're working on your homework and you see population standard deviation, you're a really good student. So you go to your notes where it talks about population standard deviation and you try to use this formula. Don't do it, okay? Use your calculator. This is a little bit easier to do by hand if we were doing it by hand, but since we're not doing it by hand, I kind of like talking about this because this formula matches the definition. Sample standard deviation, the exact same idea. It's a square root of the sum of the deviations, but since it's for a sample, how do we represent the population mean? It's the sample mean now, it's x bar. But since it's a rough estimate and not an exact estimate, instead of dividing by n, the sample size, it divides by n minus 1. Okay? Note here, if you were doing it by hand, you wouldn't round into the very end and use as many decimal places allowed by your calculator. Go ahead and flip this bad boy over. So what do I do? I make you do it once by hand. So you think I'm the nicest teacher ever for letting you use your calculator, right? So I'll show you that you're capable, you're smart enough, you get it, but so many computations leave so much room for error. So even if you know what you're doing, but you just miss one little thing, whole problem's off, okay? So let's see if we can't do this by hand once, and then I'll say, okay, let's just do it in our calculator real quick. So the first thing we need to do is we need to figure out the sum, because we need to know the sum in order to find the mean. So what we're going to do on our calculator is add up 2 through 10 real quickly, okay? I'm going to blow my nose over here. Once you get the sum, go ahead and put it down at the bottom. What do all those values sum to? You guys get 59? Okay. That means we now have enough information to figure out our average. Remember, x bar means your average. How do you find your average? You take your total, 59, and divide by how many values you have. How many values do we have? 10. So what is our average? 5.9. Again, it's an easy word problem to go with. Maybe it's the number of hours you work in a day or something like that, okay? So say on average we work 5.9 hours in a day. What would be our spread of this? What would be our standard deviation? So the first thing we need to do is we need to find our deviations. Remember, your deviations are simply your individual value minus the average. So how far are you from the average? So when I was in college, I didn't work a whole lot. I worked maybe 12 hours a week, like 2-hour shifts at the campus copy express. So I was like your copy person, okay? So what I would do is I would say, okay, I work 2 hours minus my average of 5.9. That's a deviation of negative 3.9. It means I work 3.9 hours less than the average. Number 2, do we even need to do the math there? No, because it's the exact same value, so we can just put negative 3.9. All right, say you work 3 hours in a day. How many deviations would you be off? Just 2.9, and again, they're negative because you're working lower than the average. 5, how many deviations would you be off? Just 0.9. Is that all right? So 2, 3, and 5 all have negative deviations because they were lower than the average. Then there's these people that are stepping it up and making the average higher than it is, where you worked more than the average. So all these deviations are going to be positive. So 6 minus 5.9, is that just 0.1, guys? I don't need to do the calculation twice, so I'm just going to put 0.1 right there behind it. 7 minus 0.59, or 5.9, excuse me, is 1.1. 8 is going to give us 2.1, right? And then, guys, we jump up to 10, so that's going to jump us up to 4.1. Do you see what I'm doing? I'm just finding how far are each of these individual data values from the average of 5.9, okay? So anything negative means they were lower than the average. Anything positive means that's how much more than average they were. So those are the deviations. So why can't we just add those up and divide by 10? Because the negative deviations will start canceling with the positive. And they'll start canceling and give us a sum close to 0, which means, oh, we don't deviate at all. So what's one way to always get rid of negatives? Squaring, okay? So the squaring is a necessity only in the fact that it needs to get rid of negatives, so negatives don't cancel out with positives, okay? So all we're going to do is take these numbers over here, but what happens when you square a negative? It becomes positive, and right there, guys, we've gotten rid of the negative deviations. Just real quickly, guys, I'm going to write them all down here just because I think you get what we're doing. Negative 2.9 squared. I'm just taking this column, the deviations, and squaring them. 8.41. Negative 0.9 squared is 0.81. 0.1 squared is just 0.01. 1.1 squared is 1.21. 2.1 squared is 4.41. And this is what I was talking about. If these were really ugly numbers, you wouldn't be rounding. You'd have like 3, 4, 5 decimal places. Try to be as accurate as possible. I think these are not rounded yet, so we're okay. All right. We're almost there, guys. Make sure you write them all down. Notice all of them have become positive because when you square negatives, you become positive. So it kind of just shows you a negative 3.9 deviation, and when you square it was 15.21, It's pretty similar to a 4.1 positive deviation, 16.8, right? It's just showing you that distance is about the same, just on one you were lower, on one you were higher, okay? So the negatives won't cancel out the positives. So the last thing we need to do before we throw ourselves into the formula, remember this big sigma just means sum up all the squares of the deviations. Well, this whole column was the squared deviations. So all we need to do is that. If you trust me, I'll do it for you. Beeper bopper beep. 78.9. Okay, all we did was just add those all up. So where are we sitting at right now? We're sitting at that, if this really represented the number of hours worked in a day, the total sum of the spread is 78.9. But we want to know the average, right? And so how do you have an average? You take that and divide by your sample size. So since this was a sample standard deviation, guys, I'm going to just rewrite the formula from the other page, okay? It was S equals a big square root, sigma of x little sub I minus x bar, the quantity squared, all over little n minus 1. Can you guys see that? So I'm just stealing that from the other page, all right? What we're going to do is we're going to take the sum we just found over there, 78.9, and divide by n minus 1 and get the square root. So this is just the square root of 78.9 divided by 9, because it was 10 minus 1. Is that okay if I just go right to it? 78 divided by 9 is pretty repeating. It's 8.76 repeating. I'll move my hand so you can see that. 8.76 repeating, but when you take the square root, you're at about 2.96. The same rules kind of apply for standard deviation. They'll tell you, but 2.96 is good, and we'll put units there. So what does that mean? It means if the average work hours a day were 5.9 hours, on average, each of us work about 3 hours off of that average, on average, right? Some of us are spot on, some of us are further, but on average, we're about 3 hours away from that average, and that's all it is. It's the distance there. So how many of you guys want to do that every time you're asked to do standard deviation? Not me, okay? So what I have for you, and some of you might already know it who's done stats, is I have a calculator cheat sheet. So this is the Chapter 3 calculator cheat sheet. Guys, this will get you through Chapter 3. So it actually will help you with mean, median, mode from the front, and it will also help you with the stuff we're doing on Monday, okay? So don't get rid of this. And remember, you're not allowed to use these in the test, so by the time you get to the test, you're not going to need it. Am I short? Did I get an extra one somewhere there, guys? Yeah. Okay. All right. Can you pass it back to her real quick? Everybody get one? No extras? All right. So get your calculator out. I'm going to try to do it on the screen, but I don't know. So even if you don't have a calculator, make sure you follow along and put notes on there. Let's do it with this data. Okay? So if you look at your calculator sheet, it goes, I need stat. Using your calculator to figure out statistics for one variable. So let's not use that example. Notice how I gave you like a 5-digit example. Let's use the R values that are in our notes if that's okay. The step 1 says you must enter your data into your list, okay? So I'm going to put this on. I don't know if it's going to help or not. Is that okay? It's a little bit of a glare, but all right. So what we have to do is we have to go to list 1. List 1 is always right here, but we're going to hit stat. Notice edit's the very first thing highlighted. That's what we want. Hit enter. And here you have a bunch of lists. So real quickly, you're going to see if somebody's used your calculator, whether or not, or even if you haven't, somebody has, okay? So notice I have stuff in my list. Even if you don't have something in your list, pay attention, because you're going to eventually have stuff in your list that you need to delete. So anytime you need to clear out your list, you go and highlight it, list 1, and just hit clear, and then enter, and it clears out your data. Okay? Don't hit delete, because you literally delete the whole list. The list disappears, all right? I can get it back for you, so if that happens, let me know. All right, does everybody have their list ready and cleared? At that point, just enter your data in. It does not have to be in order. This happens to be in order, but it doesn't have to be in order. So we'll just do 2, enter, 2, enter. And what's nice, it kind of just keeps a running total. So notice it has list 111. That means in list 1, it's ready to put in the 11th data value. So I know I've put in 10 data values. So at least I know that I put in the right amount. Hopefully I put in the right numbers. Guys, entering your data in like that is going to be the most cumbersome part of the problem. It really is. So take your time and make sure they're the right numbers, because the second you enter in a 100 versus a 10, we know what's going to happen, okay? After you enter your data, you're going to go to stat again. But now we want it to actually calculate something. So scroll over to calculate and hit one variable stats. And this is where we kind of go different ways. If you have an older one like me, it just has one variable stats. If you have a newer one, it asks you which list do you want to find the one variable stats for. So you tell it which list. Hopefully, does it say list 1 in there already? Okay. And the frequency would just be left blank, I believe. Or I think you can put 1. I think you can leave it blank. Us that have it, if we want stuff in list 1, that's an automatic default. But notice, guys, all above our numbers, see how you have L1, L2, L3? Anytime you want a different list, you can put it behind it. So like say I want it to look at list 1, I hit second 1, so I know it's going to be looking at list 1. That's the default. You don't need to do it for list 1, but maybe I have something in list 2 and list 3 I want it to look at. I would hit second 2 and it would look at list 2 for me. You hit enter, guys, and magic happens, okay? Why? What does X bar stand for? Sample mean. What do we find our sample mean to be? It did it for us. You do not need these 2 values here. You're never going to use these 2 values here. But what does S stand for? Sample deviation, standard deviation. What do we find our sample standard deviation to be? 2.96. What did this say it was going to be? 2.96. If it wanted population standard deviation, what would we use? The sigma. Notice it's a little bit different because instead of dividing by 9, you would divide by 10 there. So this is what I was talking about. It will do it for you. You just need to know when it says it's a sample and it asks for standard deviation, you need the S, okay? But if it's a population and it asks for standard deviation, you need the sigma. See this little arrow right here? You know what that means? We can arrow down. Look what else it has for you. Guess what MED stands for? Median. So notice everything we did in 3.1, our mean and median, we could actually do in our calculator. You can throw all your data into your calculator, hit one variable stats, it will give you your mean and your median. What's the one thing it doesn't do for you? Your mode, okay? There's a way to kind of get around it, but it's more cumbersome than helpful, so I don't really worry about it, okay? So, guys, from here on out, this is how you're doing calculations, okay? How do we do it? We go to stat, we enter our data into our list, okay, it's there. So you go to stat, calc, 1, and all of it will be right there for you, okay? What does standard deviation actually tell us? It tells us, on average, how far each data value is from the mean. On average, how far each data value is from the mean. The smaller, more compact. The larger, more dispersed. Okay? And that's just kind of a keynote of how to interpret it. So on average, how far each data value is from the mean. So in this instant, if it really was the hours we worked in a day, then on average, we're about 3 hours from the mean each. Which is pretty small, so we know all of us are consistently working about the same amount, all right? If it was large, we just know that our data is more dispersed and it's not as consistent, okay? So let's do this last little thing here. Honestly, guys, variance is almost obsolete anymore. If you had to do it by hand, you would technically be finding variance first, and then once you took the square root, it was standard deviation. So basically what we did up here, this 8.76 repeating before we took the square root is what variance is, okay? So it's needed because if we were doing things by hand, we're finding it, but it's not used a whole lot, all right? So variance really is simply the square of the standard deviation. So notice the population is literally the sigma squared and the sample is literally the F squared, okay? It's squaring the standard deviation. So it wants to know the sample variance, so it wants to know S squared. So that is S squared. Is everybody okay with that notation? Okay. So this is the same data set as above, same as above. But notice how we have it in this calculator now, and we have it to more than just 2 decimals. That's what we want to do. We want to write this down to like 5-ish decimals, because the more accurate our answer will be. So let's write down, what is this, 2.96086, like that. Is that okay? So I'm just taking that 5 and turning that to 6. So 2.96086 squared. Throw that into your calculator. If you have an older one, like I think mine allows me to type it right below it. If you have a newer one, it disappears. So we get 8.767. So we would round that to 8.77 units squared. So what we do, guys, our variance is not given to us in the calculator. So what we do is we take our standard deviation of the calculator and square it, okay? So if it wanted population variance, we would take sigma to like 4 or 5 decimals and square it, and we would get sigma squared there. All right, let's do this, last one, and we're done with 3.2. I'm going to cut you off. I know it's a lot.